Today we'll discuss how to start directly from observational data, like the kind you could extract from video, to calculate quantities from that data that describe the motion, to combine that with some knowledge of system properties, and then to apply our fundamental principle, Newton's second law, in order to determine the total pushes and pulls from the surroundings that are responsible both for speeding up, slowing down of the object, as well as curving of the object's trajectory. All this can be done without knowing what's pushing or pulling on the system. However, after we finish the analysis, the knowledge we obtain about the net force will help us to make some reasonable guesses about the nature of the interactions of the system with the surroundings. Here's what we know about the motion. We have a CSV file containing the x and y positions of our system. We show the first few entries here. You can download the file from the link that should pop up now. As always, we encourage you to try the analysis we discuss here on your own. The mass of the system is 0.15 kilograms. The identity of the system is otherwise unknown. The position data was sampled at regular time intervals of delta t equals 0.05 seconds, and the starting time for the observation was t equals 0. Let's first sketch out by hand a procedure for using this information to determine the net force. From the first two position data points, we can estimate a velocity. Then, from there, in order to go further to estimate a velocity change to get at the net force, we need a third position data point to obtain another velocity. So from the first three position data points, we estimate two velocities. And from there, we'll get one estimate of the change in velocity, delta v. Now, by multiplying this delta v by m, we then obtain an estimate for the change in momentum, delta p. So now we can calculate our first estimate of delta p over delta t, as we have written here. And now, by applying our fundamental principle, Newton's second law, we also have our first estimate of the net force. We can get our next estimate of F net, a time interval delta t later, by taking the next position data point and repeating this process. In other words, with the new position data point, we compute a new velocity, which is now our new final velocity in computing a new delta v. Our old final velocity from the last calculation becomes our new initial velocity in this calculation. So we obtain a new change in velocity, delta v, then from that a new delta p, and then a new delta p over delta t, and therefore a new estimate of F net, that is delta t later in time than our last estimate. We can keep repeating the same procedure over and over again until we run out of position data points. We can see that doing this by hand would be very tedious. So let's use the computer to help us with this repetitive calculation. Let's discuss the main features of the program that we'll use to help us do the data analysis. To help you get started doing this analysis at home, you can download a starter program using the link that should pop up now. Much of what we discuss here will seem familiar from our past work in building computer models. For example, the program setup shown here is nearly identical. However, let's be very clear. In our past work, we started from initial conditions and models of the net force, and we made predictions of the motion future. That's not what we're doing here. Instead, in some sense, we're going backwards. We're starting with full knowledge of the motion and using that to compute motion quantities, ultimately computing delta p over delta t, and then, through the use of Newton's second law, we can learn about the net force acting on our system. To do this now, we first need to insert the system and motion information we already know into the program. Here we put in the system's mass, the time between the observed position data points delta t, and the starting time for the observation. Next, we need to read in the position data from the CSV file. These lines of code do that and will work for any CSV file in a 2-column format with the X positions in the first column and the Y positions in the second column. The variables capital X and capital Y are lists, which, as the name suggests, contain the data in an ordered fashion. A particular data point can be accessed using an integer index. You can think of the index as playing the same role as the subscript for position vectors, R0, R1, R2, etc. So, for example, the X component of R0 is capital X0. The Y component for R1 is capital Y1, and so forth. We will use a variable for the index, which we will call here IDX. Then we'll change that as we systematically calculate motion quantities. Let's put that to use right away now by estimating all the velocities we can from the position data and using our knowledge of delta t. Here we create new lists to hold the X and Y components of the estimated velocities, and then, using a while loop, we step through all the position data points, using the index as the loop variable. In the loop, we calculate each velocity component separately. Here we show the correct code for calculating the X component of velocity, first calculating the X displacement, then estimating the velocity from the displacement divided by delta t. The lines of code for the Y component of velocity need to be edited to do this calculation correctly. Pause this video and see if you can write down these lines on your own. Here's one way to correctly compute the Y velocity component. Let's note a couple of points here. First, notice that we are doing calculus here. We're obtaining our velocity estimates by estimating the derivative dr dt using the displacement delta r divided by delta t. We'll compute a few more derivatives shortly in the same manner, and we'll say a bit more about approximating derivatives in this way at the end of this lecture. Second, we also notice that for each velocity estimate made this way, 2 different position data points are needed. You'll recall we said earlier in this lecture that we need 3 position data points to calculate 2 velocities. What that means in general is that for a given number of position data points, the number of velocity estimates will be 1 fewer. For that reason, we defined our lists for velocity components to have 1 fewer entry than the number of position components. We determined the number of position components from the X list using the Python function len. Now we can calculate motion changes that we can connect to the net force. We do this in the main calculation loop here, where we reset our index variable and once again use a while loop with the index as the loop variable. For each value of the index variable, we first form velocity vectors v initial and v final from the velocity components in the lists. The code shown here does that correctly. Now we need to go through all the steps to obtain delta p over delta t. First, determine the corresponding momentum. Then, compute the change in velocity and the change in momentum. Then, estimate dp dt from delta p over delta t. And finally, apply Newton's second law to obtain F net. Pause the video and see if you can write out the code for all of these steps. Here they are, where we remembered here to use the variable ball.m that we defined earlier to represent the system mass, 0.15 kilograms. Just for emphasis, it's this step where our fundamental principle, Newton's second law, comes into play. Everything we calculated before this step was obtained directly from the data and directly describes the system and its motion, the velocities, the momenta, the changes in velocities, and the changes in momenta. It's right here where we use a secret of the universe to link these system observations to the influence, the interactions from the surroundings acting on the system. We can push this further by calculating the quantities that describe the speeding up and slowing down and/or curving of the trajectory, and linking those to the total pushes and pulls along those directions. So, first, to describe the speeding up or slowing down, we need to calculate the parallel component of dp dt, which is the derivative of the magnitude of the momentum with respect to the time multiplied by the unit vector p hat. Pause the video and see if you can write out the code for these steps. Here's one way to write this. Notice the derivative we're approximating involves the magnitude of the momentum only. It's the change in the magnitude, the final momentum magnitude minus the initial momentum magnitude divided by delta t. Once we have dp dt parallel in hand, we again use Newton's second law to connect the total pushes and pulls along that same direction. Next, we can now describe the curving of the system's trajectory by computing dp dt perpendicular. We can do this in one line of code. See if you can select the line of code that works here. Here's the correct way to do this. Now, if you selected an answer that uses this expression, that won't work because we don't have a way to find r, the radius of the kissing circle. Instead, our correct response uses the fact that we already have estimates for dp dt and dp dt parallel. And so, since the vector dp dt must be equal to the vector sum of the parallel and perpendicular parts, we use vector subtraction of quantities we know to obtain the unknown delta p over delta t perpendicular. And moreover, we use Newton's second law to link delta p over delta t perpendicular to f net perpendicular. Now at this point we could solve for the radius of the kissing circle. We won't show that here, but you are welcome to try this and, if you like, discuss how to find this radius in the class forum. Before we run our program to do all these calculations, let's point out that we already have included code to draw arrows to show f net along with f net parallel and f net perpendicular. By looking at our position data in the CSV file, we notice that the object's position will range over a few hundred meters, which means that to make the arrows visible, the arrows need to be several tens of meters in length. A value of arrow scale like that we show here works for that. Now let's run the program. The analysis of the motion tells us that the net force, represented by the yellow arrow, roughly has the same direction throughout the motion. On first glance, the yellow arrow points roughly downward for the entire motion. The black arrow, representing f net parallel, initially points opposite to the direction of the motion, but later points in the direction of the motion. The blue arrow, representing f net perpendicular, shows us the direction in which the trajectory curves. The blue arrow at every instant in time points to the center of the kissing circle that, at that instant, fits the trajectory smoothly. The visualization shows us qualitatively what f net parallel, and f net perpendicular are doing. We can obtain the quantitative values by inserting an appropriate print statement inside the loop and looking at the values in the output window. Now we don't have any further information on what agents in the surroundings are the sources of the net force. Even so, we could still make some reasonable guesses. For example, the shape of the trajectory and the direction of f net suggest that the system behaves something like a thrown object, a projectile. From this suggestion, we might try to see if f net behaves as if it were due to a gravitational interaction, like the weight force acting on the object. How about checking to see if f net is really constant and might be due to a weight force that is proportional to the mass of the system? Can you find a constant of proportionality? Try this and see what you can learn. We'll defer further discussion about this to the class forum. We'll close with a final note of caution. In our analysis, we approximated derivatives by computing differences between quantities that are nearly the same. For example, the magnitude of the final momentum and the magnitude of the initial momentum will be close to one another for delta t small for every iteration. Differences between quantities that are nearly identical are sensitive to uncertainties, so that if the observations have significant uncertainties, then our estimates of derivatives, which are done approximately by the delta of that quantity divided by delta t, may not be very good. In this problem, we used synthetic data that was carefully generated to minimize uncertainties. However, if you try these approximations on real experimental or observational data, you will need to be aware of such difficulties. And, as always, feel free to bring any questions you may have to our class forum for further discussion.